Now that we have a bit of an intuitive sense of the sort of things that correlation can be used for, what it looks at, what it looks for, we may want to develop a bit more of an understanding of how it actually works numerically and how we can use it as a measurement to describe things in a bit more of an exacting manner. Because without seeing all those definitions in the last section, a lot of times correlation is somewhat intuitive, somewhat guessable, really, that you don't need to know what positive and negative correlation are to understand or at least assume that the overall health of your relationship is probably positively correlated to the amount of gifts you buy your significant other on their birthday, and negatively correlated to the amount of time you spend away from them. It's a maybe very commodified way of looking at a relationship, but what can I say? Statisticians are very commodity-driven people. We like our numbers. But, so what? You just have that intuition. Maybe it's good, maybe it's not, and even if it is, you still want to get more detail for how useful any of that is. If it's particularly strong, if it's particularly weak, and that is where we talk about the thing called the correlation coefficient, which is essentially a way to quantify that kind of relationship. In this context here, in this class, in this chapter, we're going to focus on a thing called the Pearson linear correlation coefficient in particular. A lot of our work in this class comes down to things that Pearson did about 100 years ago, but so it's the one we're focusing on. It's not necessarily the only one, but it's the one we're looking at here, where what that describes essentially is the linearity of a relationship. And if we talk about it in terms of populations, do not use the letter P. That is the Greek letter rho, up to my bad handwriting, lowercase rho. It's not my favorite notation in the world. It causes more problems than it solves, in my opinion. Just be careful with it. I once spent an entire semester calling that P, so I understand if you get it wrong, but that is actually the Greek letter rho. Anyway, we're not going to do a whole lot with rho itself. Mostly what we're going to be looking at is the sample correlation coefficient, linear correlation coefficient, Pearson linear correlation coefficient, R, which has been used in some other contexts, has been used in a lot of places. You just didn't know that's what they were talking about. It's a very important one. But R has the not-so-nice formula n times the sum of the product x and y minus the product of the sum x times the sum y over the square root of n times the sum of squares of x minus the square of the sum of x times the square root of that same sort of thing, n sum y squared minus sum y quantity squared, which is a really nasty formula, really nasty sum of things, sum of things, under radical of things, divided by sum of things. It's not very nice. I do trust that all of you guys have, at this point, the mathematical maturity to be able to compute the value R, but hopefully at this point you understand that I'm a fairly reasonable person. I don't expect you to do that. It's not a good use of your time. Certainly not this far in the semester. Wouldn't have been at the beginning of the semester either, but definitely not now. It's good to see. See at least once. And you can see with all these square roots and sums of things, you might get in your head that there's sort of a standard deviation-like flavor to this, and there kind of is. But I don't really care if you know this formula. I care even less than other ones I've talked about just because it's such a mess. And most of the work you'll be doing here, I would recommend using a calculator for, or some sort of computation software. Still, it's worth seeing this guy once, but understandably, it's not the most obvious and it's not the most convenient to work with. So, I'm not going to expect you to work with it explicitly very often, even though I want you to get acquainted with it at least once. All that said, when we're actually looking at these correlation coefficients, we're actually looking at these values. What we get are values between -1 and +1, where if the value R is equal to -1, we have perfect negative correlation. As the value gets closer and closer to 0, as its absolute value gets smaller, we get closer to having no relationship, where at 0 we have no definable linear relationship at all. And then if r is equal to 1, we have perfect positive correlation. Now, I will say, thinking about this sort of representation here, the values -1, 0, and 1, they're not impossible, but for the most part, you can consider them as being essentially theoretical. Now, unless you're in a very specific context, like we're going to see with these quick flashing examples here, like the number of movie tickets corresponding to the cost of movie tickets, that has a perfect linear correlation that is positive, or the score on an exam as affected by the number of incorrect questions on the exam having a perfect negative correlation, usually you get something more in the middle. Very, very few things are set up to have perfect positive or negative correlation. It's more common with things like the height and the shoe size, or absences and grade, or any of these other examples, that you get some form of pattern that may be strong, may be weak, may be positive, may be negative, but those specific values of -1 and +1, they don't really happen. Not meaningfully, not very often anyway. They can, especially if they're finagled, but don't expect them. And if you get them in a context where you don't expect them, it probably means you made a mistake. That, or you have discovered something fairly important. So just bear that in mind. And I'll also say here that when we're talking about this value r, like always, the book is going to expect you to do a lot more work than I do. It's going to expect you to do this by hand. I'm going to show you what that looks like just a tiny bit, but don't bother. The calculator and tons of other softwares online have much better, more efficient, more useful built-in computations for doing this stuff. In particular, I'm going to focus on the linear regression linreg computations in the calculator when we're looking at examples, and that's what I would say you should really learn. But we'll see that next.